Okay, and I also want to acknowledge my collaborators on this work, Valentin Bickel and Matt Siegler. So the motivation behind this work comes from our interest in lunar polar volatiles. There's been various research indicating that icy polar regolith could be responsible for reduced crater depths, reduced crater slopes, subdued topography, and even mass wasting features. And in this work, we're interested in how icy polar regolith could affect crater shapes and mass wasting for craters formed on slopes. These different morphometric properties can give you a clue about where ice is distributed or how much ice there could be in the subsurface. But in order to use morphometric properties as a clue to what's below the surface, we need a really detailed understanding about the shapes of craters that are ice-free at the dry, non-polar latitudes. So different numerical simulations and also lab experiments have indicated that topography has an important control on the final shapes of different craters. So that's what's illustrated here for a couple of lab experiments. What you see from left to right is the slope of the target terrain is increasing. And as it becomes more steep, you can see in the planar view in the top, the shapes of the craters become more elongated. And then corresponding to that below in these cross-section views, crater depths begin to decrease, your rim morphologies are less pronounced, and eventually the crater is more or less unrecognizable. But these impact experiments are for craters formed in dry terrains, and we're interested in what happens when you introduce volatiles into the picture. So to address this question, we're analyzing small impact craters. They're all about 100 or 150 meters across or less. It's important to be using small craters for this analysis because they're smaller than the spatial scale of the local target topography. And we're comparing crater morphometries at non-polar regions where ice is not stable to craters at polar regions where ice could be present. So to analyze crater elongation, we're looking at the ratio of the crater diameter in the downslope direction to the crater diameter in the across slope direction, which is something we measure from 2 to 5 meter DTMs, digital terrain models. And so obviously by this equation, if your elongation value is greater than 1, it indicates that the crater is elongated in the downslope direction. And also for this analysis, we're assuming that present day topography can be a good proxy for the target slope when the crater formed. So we're estimating target slope from the topography just above and below the impact crater itself. And so right now we're able to identify 3 independent crater classes. So your first class is sort of your typical crater. These are craters that form in level terrains. You can see that the crater rims are relatively well preserved. But again, we're more interested in craters that formed on slopes. So these are your class 2 and class 3 craters. You can see that their shapes have more asymmetrical profiles. The crater rims are less well preserved, and eventually in the class 3 craters, you can sometimes see these sort of wall terracing features on the upslope wall. Oh, and I should say that we're interested in when these transitions occur, both for regolith that could have ice and then also dry regolith as well. So right now, we're finding that there's a pretty clear transition between class 2 and class 3 craters by analyzing the morphometry or the shapes of these craters. Specifically, what we find interesting is that the craters tend to transition to class 3 at relatively shallower polar slopes than relatively steeper non-polar slopes. So these are angles of 10 and 15 degrees respectively. So perhaps this suggests that the presence of volatiles or very cold regolith could promote some sort of slumping or rim degradation on relatively gentler slopes. We're also looking at the distribution of elongated craters in both the nonpolar and polar populations. For the nonpolar, for the dry craters, we find that 55% of the sampled craters are elongated in the downslope direction. This is important because it underlines that target topography has an important factor, an important role in the final shapes of craters, even in nonpolar terrains. But we do find that at polar terrains, the percentage of craters that are elongated is slightly higher Specifically, 67% of the sampled polar craters are elongated in the downslope direction. So again, maybe this is telling you something about the role that really cold regolith or potentially volatiles has in affecting run-out distances or final crater shapes. We look at how crater elongation, which is mapped now on the y-axis, can be related to mean annual temperature. Mean annual temperature is a really good proxy for the subsurface ice stability. So you can see there's a super amount of scatter. So mean temperature is not predictive of polar crater elongation. But we do find it interesting that the most elongated craters, meaning the craters that have values of elongation greater than 1.2, those dark blue craters are often in ice stability zones. So potentially for the coldest regions where ice could be present, this is contributing to the relatively enhanced population of elongated craters that we find at the poles. There's an important caveat to mention, which is this specific plot was derived from the diviner models that are about 2 times the spatial resolution of the craters that we're analyzing here. So you're going to have some contamination from the areas around the craters, which are generally warmer than what you have in the crater. But we're really excited now to be working with Matt Ziegler, and he's produced these high resolution thermal models, essentially at the spatial scale of the 2 to 5 meter DTMs. So right now we've been analyzing the craters in the Viper primary mission area using his thermal model. So we look forward to having a higher fidelity correlation for you. So a couple important implications I just wanted to point out is because we're measuring elongated craters both at non-polar dry terrains and then also polar potentially ice terrains, this suggests that not accounting for target slope could result in overestimating both the runout distances caused by icy or wet regolith, and then also any shallowing related to subsequent infill by volatiles. It's also important to remember that any sort of volatile-related shallowing could occur during the impact formation process. That's what's illustrated on the left here. A crater that forms an icy target is going to be preferentially shallower than a crater formed under the same impact conditions in relatively drier terrain. And then volatile-related shallowing can also occur after the crater forms as volatiles infill and modify the topography. As we continue this analysis, wanted to point out that we're looking forward to some future missions. Elongated craters on polar slopes could be good candidates for identifying ice exposures revealed by mass wasting. So more observations by shadow cam or Trailblazer could be interesting component to this analysis. And of course, the science here is highly relevant to the Artemis 3 science objectives, understanding planetary processes and the character and origin of lunar polar volatiles. So in conclusion, our initial results so far show that elongated craters are on steep slopes all across the moon. This again underscores the importance of accounting for target topography before you start using morphometric properties as a probe for understanding volatiles in the subsurface. But it is interesting that we find elongated craters tend to be more common on polar slopes than on non-polar slopes. And they also appear to transition to class 3 more degraded looking craters at shallower slopes in comparison to their counterparts formed on steeper slopes. And thank you very much.
Awesome. Questions for Ariel? Okay, cool. Bill, go ahead.
Let's say you have can you say something about how the degree of slumping is correlated and how much takes that? Like imagine you just got a model.
Yeah, exactly. It's something we haven't done yet, but are interested in working with. Actually, that ice sail plot I showed earlier. It's basically a trade-off space between ice abundance, how deep you're burying it, your impact conditions, of course, as you know. So that's a project we're working on. And I don't have the constraints for you now, but it's an interesting parameter space.
Yeah. Do you even have like a ballpark? Would it be like 1% ice, or like even smaller percentage ice in the regolith just to get a certain degree of slumping? I was just saying, like, if you're going to take a shovel and dig,
Right.
how much ice would you get?
I don't know, but
Okay.
I will also say that if Dana is here, anyone from the Razzle team, I saw that they were going to be doing those impact experiments into icy regolith with the gun at Ames, I think. So maybe they'll help provide some constraints too.
Okay, thanks.
Thank you for the question. Have you tried correlating crater elongation and soil temperatures? We've looked at the diviner data for mean annual temperatures. We haven't looked at soil temperatures. Again, we're looking right now in the Viper area, which is mean annual temperature too, but we don't, so no, but we're interested in the correlation with temperature.